Hello, this is example for heat pump Carnot efficiency. And we know when we talk about Carnot, that's the most ideal situation where we're gonna get maximum efficiency. So quick recap on the Carnot efficiency. So we have this heat pump, TH and TL, and for this thermodynamic cycle, we require the work coming and we achieve the heat transfer from lower temperature to higher temperature. So we have QL and the QH right here. And for the Carnot efficiency, we actually don't use eta, right? We're using coefficient efficiency of performance. So for heat pump and the maximum, the formula is what's desired. We desire more and more heat transfer to the house, which is on this side, right? And this is outside. So we want more and more heat transfer to house, that's QH, that's corresponding to higher temperature, TH. And required work coming. And the required work is going to be QH minus QL, so that's TH minus TL. So there's a video about the COP for heat pump in the previous one, so take a look at how this equation was coming up. And once we know that, we can go ahead and find the maximum COP for heat pump. Now let's look at this problem. They said the building is maintained at 21 degrees, so that would be our TH at 21. And the temperature, outside temperature is -5 degrees. And there's a transfer heat rate of 135,000 kilojoule per hour to the house, so that would be corresponding to our QH, 135,000 kilojoule per hour. I mean, it should be more theoretical. This should be a dot because divided by time, right? So in that situation, we can put all dot here. Now, let's go ahead, solve this maximum COP. We know TH, the higher temperature reservoir, is 21. But we have to change that to Kelvin. Again, this have to use Kelvin degree. Have to change it. And then the bottom, TH minus TL. TH is 21 degree and TL is -5. And here, since it's temperature difference, we don't need to plus 273, right? And W get the same results. Then when we calculate that, we will get value of 11.31. That's the highest or maximum or Carnot heat pump coefficient of performance. Then because when you get this maximum value, you will get the minimum power required, right? So thinking about another formula we're talking about for in reality, if in reality is actually at the ideal situation, we know in reality COP formula is using our desired, which is QH, over required, which is our work in. And I'm going to add up for both of them. We divide by time on both top and bottom of the fractions. And we do know for this one, our QH is 135. That's how much heat transfer rate is pumped into the dwelling, into the house. And we also know in this situation, it's the most ideal. It's like a fairy tale situation, and your COP is performing at the highest level, which is 11.31. Okay, in reality that does not happen, right? But this one we said what would be the minimum required, so that will be get you the minimum value of work in. That's minimum value. So then when we calculate that, the required work transfer rate will be equal to, and we can also change this kilojoule hour to watt. In order to do that, we're going to see 1 hour is going to be equal to 3,600 seconds, right? Then that will give us hour canceled out. We will get the unit of, basically it's kilowatt. If we do that, and our W in is going to be equal to 3.316 kilowatt. So that's required input from compressor, required work. Okay, so this is an example of using Carnot efficiency for heat pump. All right, see you next video. Bye.